isentropic process, isothermal process. Now you just imagine that now your flow is going through an isentropic process, constant velocity. That's the difference. Right? Thermodynamics usually is about things that are not moving, or the kinetic energy is not very important, so you can look at thermodynamics. And thermodynamics will tell you what's possible or what's not possible. Right? For example, the other day we talked about stagnation pressure loss, right? Because the stagnation pressure can only lose. It cannot win by itself unless you do work on it. What we are talking about is kind of the pumping process or compression process. Then your system of gas can gain energy because when, for example, when it's compressed and someone is working, right? So that's when you can get it. So the system itself cannot gain energy. Right? For example, thermodynamic second law will tell you that water flows from the high place to the low place. Right? If you want to have that perpetual water flow in your backyard or in your house, you need a small pump to pump the water out there and it will flow. Right? So you don't see the water flow outwards by itself. That's thermodynamics. It's not possible. So even though you have that process, supposedly when the water is flowing, there's a velocity. Right? So that is the process that involves some kinetic energy. But just as the process itself, you would know that's not possible because the system cannot get energy by itself, right? And the entropy can only increase, and entropy cannot decrease. So what you have here is the first question is that if the volume is reduced by a factor of 3 through an isentropic process, what is the change in entropy? Well, 0. So you can say, well, this is sounds like a trick question. If you want us to know whether it's 0 or not, what do you ask is increase or decrease? So the answer is neither, right? So it's already said isentropic process, so there will be no entropy change. Second, what is the pressure change? Now you use your isentropic relationship, which is P2 over P1 is equal to rho 2 over rho 1 to the gamma, or you reverse it, volume 1 over volume 2 to the power time. So that's 4.66 times. That's very straightforward. Part C, if the above volume change takes place under isothermal conditions, what is the entropy change? Now, isothermal is not isentropic, right? So you would expect the entropy to change, right? So we put it in there S2 minus S1 per volume per kilogram. It becomes minus 0.315 kilojoules per kilogram per kilogram. Right? Now again, as we talked about, this is really a funny unit. But it has to be solved. You need to have a degree K in there, right? For example, we already said if you have a system that is already very chaotic, meaning that it's already under high temperature, you put in the same amount of energy as compared to a system that is low temperature, you put in the same amount of energy. The increase in entropy is different, right? Our analogy is what? A very messy room, you don't see it messier if someone just kicks something around, right? If it's a very tidy room, you see. So the increase in entropy will be large. So now here, because the volume what? What do we say? The volume decreases because you go through isothermal, right? And you think about it, when you go through an isothermal process, usually when you compress the system, you increase the energy and the temperature should go up, right? But you say, no, I don't want the temperature to go up. So that means you have to take the energy out of it, right? You have to have all this little gremlins taking energy out of the system while you are compressing the system, right? So what does that mean? You say, well, if the temperature does not change, why would entropy change? Now think about it. You think about it. This again could be very much like your room, right? Let's say you have a whole bunch of things around your room, not necessarily scattered all in a mess. But let's say you have a flower pot here, a book there, you just put it as where it should be. But then one day you say, well, I'm going to consolidate this thing. I'm going to put everything on a bookshelf. Everything, including books, a small plant and so on. And all of a sudden it becomes really tiny. You put those things that are supposed to be in the whole room, now it's only 1/3 of the room. So your entropy decreases because your room becomes tinier, right? So even if the temperature does not increase, even if you take away the energy, while that happens, then you have the entropy decrease. So you would have a minus sign because it's log of 1/3. And part D, if the volume change takes place under constant pressure conditions, what is the final temperature? Right? If it's constant pressure, you see PV equal to RT, and if P is constant, and of course for the system R is constant, then your temperature change is proportional to the pressure change. So think about it, if you have a system and your pressure is going to be maintained the same, how would that do? For example, one thing you can picture is that if you have a balloon which will be under whatever pressure in the atmosphere plus the stretch force of the material, right? So usually in a balloon, your pressure is higher than your empty. But you say, I want to maintain the pressure to be the same inside, but then I want to decrease the volume by 1/3, or to be 1/3. Then what will happen? You cool it. You cool it, then it will shrink, right? Because there is thermal expansion, and when you cool it down, it becomes small. And so you want the pressure to be constant, but you want the volume to be smaller. And you need to decrease the temperature in such a way that the temperature will be only 1/3 of the original temperature. And this can still be the absolute temperature, right? You all need to convert it to Kelvin. You cannot just use degree C. For example, if your system started out at 0 degrees C, and you say 0 divided by that, how do you do it? So it has to be absolute temperature. So your absolute temperature will become 1/3. Let's say if your original system is under the room temperature, about 300 K, this means that you need to go down to only 100 K, which is really freezing, right? Yeah. Some gases probably already become liquid. For example, CO2 would have become liquid. Nitrogen would not. Nitrogen will become liquid when it's about 77 Kelvin, so it's below 100 Kelvin. Right? By that temperature, when we go down to a temperature that low, you are already talking about things like cryogenics. Somebody interested in the future in working on rocket propellants and hydrogen, liquid hydrogen, right? How do you get liquid hydrogen? Even colder than nitrogen, because the molecule is even smaller, it's more energetic, you just heat it up a little bit. So for hydrogen, you need to cool it down even further. Right? So oxygen is about 80 something Kelvin. Nitrogen is about 77 Kelvin. So if you want to work on cryogenic, then you know how to do it, right? If you want to keep it in the same temperature, same pressure, and if you want the volume to be small, meaning that you want it to become liquid, what would you do? Cool it, right? Cool it really, really hot, then you will have liquid. Questions? Okay. Some of you asked me about the exam. I want to have the exam as a natural part of the topics that I would like to cover, and we will make it an integral, more integral, coherent way of doing it. So I'm projecting that the exam is more likely toward the end of October, but I would announce it early enough. I will not just announce it that we are going to have an exam tomorrow. Yeah. I will announce it at least 2 weeks ahead of time, but Now, what I have in mind is about October 26th. Yeah. So if you want to take a notice, say tentative. Okay. I'll try to do that. Because it could be 26, it could be 28, but if I'm going to give an exam on 26, I'm not going to test you on the material I cover on the 25th. Okay, so anyway, so it's very likely that's the day. Okay? So we may have the material they cover up to October 19th, right? Or October 17th. Right? Good. Any concerns? After this quiz, you should have a little bit feeling. What I would suggest you is that if you really forget about your thermodynamics, go back and review. Some people call gas dynamics nothing more than thermodynamics of high-speed flow. In the older version of some of the books when I was a student, there was a real famous book. It's actually called Mechanics and Thermodynamics of Compressible Flow. Okay, so what you have, really, thermodynamics plays a significant role with the addition of velocity. Make sense? So you may want to review thermodynamics a little bit. And ultimately, what's useful here is nothing more than isentropic flow, isothermal flow. Or you want to keep the pressure constant, isobaric flow, right? And you just write down PV equal to MRT is constant, and these other two are inversely proportional to each other. Or is temperature constant, pressure and volume are proportional to each other. Right? So you summarize it, it's really quite easy. What the challenge is, the isentropic flow is somewhat more involved, right? Because your pressure ratio is proportional to density ratio to the power gamma. That is the power. It's not so intuitive. Right? And in your thermodynamics, you also have this thing called polytropic flow, right? Or polytropic process. Right? So usually you would not have so ideal that it's isothermal or it's isobaric or it's isentropic, right? So your PV usually has some sort of a power to it, right? Like in our isentropic case, PV to the power gamma is equal to constant. Now, so in your thermodynamics, it has a PV to the power of, probably you use a K, right? And K usually in your thermodynamics, well, K is equal to 1.3. So that means it's a sign, right? And how about K is equal to 1.33? That could happen too, right? Because it depends how much your process deviates from the isentropic condition, right? So again, one example is if you do something, if you cook something really slow cook, it's not isentropic, but it's not very far away from isentropic, right? If you cook it real fast, it's fast, right? For example, a couple of weeks ago, I learned to make cheese. And some of you are interested in making cheese out of milk. You can do it in your own kitchen. Man, it's real slow cook. We have a friend they were so kind to teach us making cheese. You cook it out to 95 degrees really slowly. So that's kind of very isentropic. Like if you boil it, you certainly will not make cheese. So, so you can see some processes like this, some processes like that. Okay. Now, again, regarding the grading, I'll talk to your TA, Justin. Other than that, let's continue on. Let me do a quick review on this conversion nozzle flow. Now, if you look at this figure that I draw, the importance of it is such that, again, you should be able to wake up in the midnight and draw this thing on the screen. Okay. If you can do that, you are pretty good shape. So, when you have a converging nozzle flow, a few things that will come to your mind. First, if the pressure difference or the pressure ratio between your stagnation pressure and your ambient pressure is high enough, you would have Mach equal 1 at the exit. And what that ratio should be? That ratio will be 0.5283 if you are talking about diatomic gases such as air. Now, the value will be different if gamma is not exactly equal to 1.4, but you can see this, right? Monatomic gas is 0.4871. So the stagnation pressure as depicted here is the pressure in the reservoir. But your pressure is not necessarily coming out of the reservoir. One thing you can think about is, if you are talking about supersonic inlet of an aircraft, then apparently your reservoir is the whole atmosphere, right? But you would have an equivalent stagnation pressure there, right? Because you are really running on, right? In a sense, it is unsteady flow because your aircraft is running on the air. But if you think about it, the air is flowing at a relative velocity, right? So, some point, if you can bring the flow into stagnant relatively to the airplane, that is your stagnation pressure. So you can consider that as your reservoir pressure, right? So now you need to be able to imagine certain things that would exist without physical existence of it, right? And also the A star. Once it's choked, you have the A star. But the problem that we had last Thursday was that A star was not there. But you imagine that's like kind of your sea level. Even you don't see it, you know that it is there, right? Now, you have learned things enough that you can picture the existence. Otherwise, there will be absolutely impossible for you to think that there is such a thing called 0 Kelvin. Because very few of us really have the experience with 0 Kelvin, right? Right? If you just go to the Costco, the vegetable section of it, it's already very cold, you know? That's probably only 270 Kelvin, probably not even, right? So 0 Kelvin, you can say, never experienced, I don't believe it. You cannot say that, right? The whole thing about this scientific enterprise is that you learn enough, and based on that, you can extrapolate, right? Otherwise, scientists could never study cosmology. You said this light comes from 270 million years ago. Too far back, I don't know about it. You cannot say that, right? Otherwise, nothing will happen. You cannot predict anything. So, you need to be able to think about that A star may not exist in your physical problem, but it's a reference value, right? And stagnation temperature, stagnation pressure are the same thing. So once you do that, you'll be able to have some interesting examples. And one example we have, of course, we already did, right? The conversion nozzle flow. Remember this, which we did. We said that in this case, your A star is really somewhere if you could, right? With the given pressure, this is what you have. Now, the problems can be framed in such a way that if you said, I already have a choke condition. For example, let's go back to this other example.